So continuing on with our introduction to Matlab Octave and Scilab, we're going to talk now in episode 5 about complex numbers. Let's go. There we go. So we will learn the following in this episode: what a complex number is. It should be a review for everybody. What the constant 1i is. Real and imaginary part of complex numbers. The Euler identity, magnitude and phase of complex numbers, basic operations on complex numbers, functions with complex numbers. So this is the point. Every number in MATLAB is actually a complex number. Every variable is complex since they're not really typed. Well, they could be other things too, but if they have an imaginary part. Now this looks like it might be a math course, but it's not really. I'm going to talk about the mathematics, but we're going to go over how MATLAB implements complex numbers and some of the functions associated with complex numbers. Complex review. There's this number I. It's the positive solution of the equation I squared equals -1. That defines what the complex unit is, I. I squared is -1. The number is also called the imaginary unit, yes. So a number of the form AI, where A is real, is called an imaginary number. A number of the form A plus IB is called a complex number. It has a real part and imaginary part. Yeah, A is called the real part, and B is called the imaginary part. Real and imaginary numbers are a subset of the complex numbers. In the same way, like rational numbers are a subset of the real numbers, etc., or the integers. So you can represent a complex number in a plane as a point in the plane, where you put the real part on what's called the real axis. Real axis is down here, and then the imaginary part is this axis here. So a point in the plane, A, B, represents A plus IB. Again, the horizontal axis is called the real axis, the vertical axis is called the imaginary axis. A point in a plane also can be represented in polar coordinates. So you could also, given a radius from the origin and an angle, that also is a way to represent a point in a plane and therefore a complex number. So using the Pythagorean theorem, you can see that R is A squared plus the square root of A squared plus B squared, which is what's just called the magnitude of the complex number. And the phase is the angle, the counterclockwise angle from the x-axis here is the angle, and that's just this arctan2. Arctan2 is a function in MATLAB or other languages that gives you the arctan function, but it keeps track of what quadrant you're in. Positive angles go this way, counterclockwise. Negative angles go clockwise. So a complex number can be written in two ways. It can be A plus IB, which we've already seen. That's called Cartesian representation. Or in polar representation, it can be written as R cosine theta plus IR sine theta. You can show that. So from that, you have this Euler identity, where that defines, we'll just say it defines E of I theta is cosine theta plus I sine theta. You actually can prove it, but we're not going to do that. You basically prove it by looking at the power series for the exponential function. If you want to understand that mathematically. But any complex number then can be written also as magnitude times e to the I angle, or real plus I times the imaginary part. some operations in Matlab. I is not used. It can be used, but the complex unit is written 1I. So it just, that is the way it looks like a number. So 1I is the same as I in Matlab, Scilab, and Octave. Any complex number can be written as a real part plus 1I times the imaginary part, where A and B are real numbers. So the function in MATLAB function complex A comma B returns A plus 1I times B. So if these are real. The function abs, absolute value, returns the amplitude of a complex number. If it's a real number, it gives the actual absolute value, but in a complex number, it returns the amplitude. Angle Z returns the phase in MATLAB, or any of these other its clones. The real function returns the real part. The imaginary part returns, IMAG returns the imaginary part. So we're going to do a little demo now. Okay, let's say A equals, let's do some simple things. We'll say A equals, I don't know, 1, B equals 2, Z equals A plus 1I times B. So when it prints the number, displays the number, if you do disp Z, it does the same thing. It says 1 plus 2I. So use math notation when you print it out, even though you have to put it this way, the 1A plus. So then if you look at, let's go over these functions one at a time. So the absolute value of Z, well, that's if you figure out, well, let's do something that's easier. Let's do A equals 3. B equals 4, Z equals A plus 1I times B. Or you could also say Z equals complex AB. You get the same result. So now if you look at that, you can say what is the absolute value of Z, and it comes out with 5. Well, it turns out that 3 squared plus 4 squared is 9 plus 16, which is 25, and the square root of that is 5. So that does what we just, the reason I picked those numbers is because they work out to be integers. So in this case, then, the angle of Z, and that's in radians. So if you wanted to, well, we'll talk about that in a future episode, but yeah, that's in radians. If you wanted in degrees, you'd have to do angle times 180 divided by pi. Whoops. What did I do wrong? Oh, angle of Z. It's 53 degrees roughly. Okay, so let's look at, so remember what Z is. We have the real part of Z. It returns 3. Imaginary part, mag, Z is 4. So those are all the function we just talked about. So now, okay. Okay, now we're going to talk about addition and subtraction of complex numbers. Whoops. Now we're going to talk about addition and subtraction of complex numbers. So to add them, you just add their real and imaginary parts separately. So this example, if you have 4 plus 3i plus 2 minus 7i, you just add the real parts 4 plus 2 and add the imaginary part 3 minus 7, and you get 6 minus 4i. That's an example. To subtract complex numbers, subtract the real and imaginary parts separately. So here's another example of that. You can just see that it works out. In general, this is sort of the general formula for adding two complex numbers, and here's the general formula for subtracting complex numbers. So we'll just do a quick demo on addition and subtraction. Okay, we have z. We've already defined that. Let's define another variable. Let's say 2 minus 6, 1i times 6. Okay, let's look at z plus w. And so 3 plus 2 is 5. 4 minus 6 is minus 2. Well, let's look at z minus w. So in this case, you subtract 2 from 3 and you get 1. You subtract negative 6 from 4, you get 10. So it behaves like you expect. Okay, now we're going to talk about multiplication. Oops. Okay, now we're going to talk about multiplication. So to multiply two complex numbers you with real and imaginary parts, you basically use the distributive rule, or some of you may have learned this by FOIL, but so you multiply a times c and a times di and bi times c and bi times di. You end up with this result. That's the general formula. And then you know that I squared is minus 1. There's a mistake here. Got to start over. No, there isn't a mistake here. Okay, sorry. Okay, now we're going to go over multiplication. Oops. Okay, now we're going to go over multiplication of complex numbers. We're just going to start with the general formula. So if you have this a plus bi times c plus di, you use the distributive law, or some of you might have learned it as FOIL. So you multiply a times c to get ac, you multiply a times di to get ADI, you multiply bi times c to get BCI, and you multiply bi by di to get BDI squared. Then you do associative law. You collect the I terms here. And notice you have this I squared here. Well, we know I squared is minus 1. So now we have this is the general formula for multiplying two complex numbers. So now let's show how you do that in MATLAB. Okay, we have these two numbers we already defined, z and w. We can do z times w. And if you look at that, so we've got 3 times 2, which is 6. And then 4 times minus 6, so it's minus 24, and then there's an I squared that's minus. So that's 24 plus 6 is 30. So this one you'd say 3 times 6 is 18, minus 18, plus 2 times 4 is 8, minus 18 plus 8 is 10, and you get the result that you expect. Okay, now we're going to look at complex division. You divide two complex using real imaginary parts. This is we're going to do this again, the general formula. What you do first is you multiply to make it simplify it. We might multiply the top and bottom by the bottom, except with this plus changed to a minus sign. And then if you multiply the top and bottom out, the bottom you have this c squared plus d squared, which is basically the magnitude of the bottom squared, times this thing up here from the rules of multiplication we just learned. And then you separate out the real and imaginary parts, and we get that result. Now this is very complicated. It looks very complicated, but it's not really. But what we will find out, multiplication and division is way easier to do in polar form than in this form. So we'll get to that in a second. Okay, now we're going to look at a little demo of that. Okay, we still have our two numbers, z and w, and we're just going to divide z by w. And whether this is, or we could also divide w by z and get a different answer. Whoops, w by z. And you get a different answer, of course. But if you look at 1 over the answer, you would expect it to be the other number, and it is. So the rules you know for division work for complex numbers, kind of. Okay, so okay, now we're going to take a little closer look at multiplication and division. Oops. Okay, now we're going to take a little closer look at multiplication and division. Again, like I said, it's easier to do multiplication and division in polar form. So if you have these two numbers here, c1, a1 plus ib, okay, error. what we got going on? What's going on here? Something's wrong. Okay, now we're going to look a little bit more at multiplication divisions, but from the perspective of polar notation, or so if you have two complex numbers, you can either be represented by z1 equals a1 plus ib1, or r1 e to the I theta 1, or zt equals a2 plus ib2 plus r2, which is equal to r2 e to the I theta 2. Then if you sort of worked out the rules of multiplication and division we already have, you can show that to multiply two complex numbers, you just multiply their absolute values, their magnitudes, and you add their phases. And to divide two numbers, you divide the amplitudes and subtract their phases. So that we'll just show that real quick. So again, we still have our two variables we defined here, and let's look at abs of z, abs of w, and what's abs of z times abs of w. So we got a magnitude, so then we can say, well, what is abs of z times w? And it's the same number. So this is showing that works. So if you look at the angle of z, angle of w. So what's the angle of z plus angle of w? So now we'll look at angle of z times w. It's the same number. So that shouldn't be surprising. So basically, when you multiply two numbers, you multiply their absolute values, and you take it e times the sum of their phases. Similarly, we can do z divided by w, and we look at angle of z minus w, or c divided by w. And now we'll look at angle of z minus angle of w. It's the same number. No surprise there. So look at abs of z divided by w. And then it's going to be equal to the abs of z divided by the abs of w. So we just show that all those properties work when we're using Matlab to do calculation. So now there's another operation you could do on complex numbers. It's called the complex conjugate. Basically, complex conjugate just switches the sign of the imaginary part. In mathematics, this operation is often represented as asterisk superscript, but it's not in MATLAB. So, but this is mathematically how you would write that. So the magnitude of a complex number is the square root of the number multiplied by the complex conjugate of the number. Matlab function has conjugate that returns the complex conjugate. So now we're going to show that. It's just a real quick demo. So we have z, conjugate, right, of z is 3 minus 4i, w, conjugate of w, oops, is 2 plus 6i. So it just changes the sign of the imaginary part, just as we've shown. So now we're going to talk about some of the functions that you can do on complex numbers. The natural log. The log of a complex number in polar form can be easily written. We take the log of r to e to the I theta. It's log of r plus I theta. So one way of seeing that is you take the log of a product is the sum of the logs of the two things. Log of e to the I something is that something. So the log of a complex number is just this. It says it makes sense from the Euler identity. So ln of e to the I theta is I theta because ln sort of undoes the exponential functions. So this is just all dividing that. So the natural log function is written log in complex. Most computer languages, log means log base e. So we'll show how you do that. So we have our z here, right? We have, we look again at abs of z. And what's log of abs of z? It's that number. And what is angle of z? So log of z, it's not surprising, it's the log of the magnitude plus I times the angle, just like we've shown, and that's something you should know about for sure. All right. Okay, now we're going to talk about a little bit more about functions and operations in MATLAB. All MATLAB functions can take complex inputs. In mathematics, less than, greater than, any order makes no sense mathematically because the complex numbers are not ordered. A complex number is not bigger than another complex number. They're different. However, MATLAB and its clones we'll take the expression a less than b, and if a and b are complex, the statement it basically gives the same result as real a is less than real b. This can result in some unexpected behavior in your code if you're not aware of this thing. I think it probably would have been better to have this be an error, but that's the way it works. If you have two complex numbers, if the numbers are complex, and you try to find if one's greater than or less than, it will only do that for the real parts and ignore the imaginary parts. So we'll show how that works. Okay, first of all, we'll show what happens. All the functions will take complex numbers as inputs. So you could take square root of z, and it'll give you a complex output. You could take sine of z. You can do a10 of z, and it'll give you something. But remember this thing we said before, you have a z and w again. We're going to do z less than w. And it says, and the answer is yes, because oh, that's interesting. Oh. Oh, that's interesting. What's going on here? Okay, I guess I'm going to cut that part out of it. Okay. So now the exercises. I want you to do this. Write a script and create a variable z and set it to any value. On set lines, use display function to write it out. Write out all of these things: the real part of z, imaginary part of z, magnitude of z, phase of z, complex conjugate of z, natural log of z, square root of z, natural log of the square root of z. Create a matrix with these values in it. Use the display function to display it. All these things, just to get an idea of what it does. And we will discuss what some of these things are in later episodes. I just want you to try them out. Okay, that's it for now. We will see you in the next one.